Droop does. Droop allows you to share almost equal current so that you also draw the supply the equal power. But it is not necessary. You also want that some converter should give more power compared to another converter in spite of both are having the equal power. That is also possible that you can carry out through Droop by choosing the right slope. Fine. So that is also possible. So entire Droop can be designed to meet your requirements. Fine. Uh, okay. So this is what Droop does. So my only objective was to just give you some overview of Droop so that you get idea that this is the typical way we control. Fine. So see, most of the converters like DC to DC converter in DC microgrid, they are controlled through what is called the dual loop PI controller. Fine. So you have an inner loop, which is the current loop. Outer loop is the voltage loop. Fine, and outer loop provide the reference for inner loop. Right? This is the very basic fundamental that also we will see in the next slide. But this is how we normally implement the Droop. Fine. So this is the Droop which is implemented without any communication layer. But there are results or there are ways in which you can incorporate communication among the neighboring agents or neighboring nodes to improve overall performance of the DC microgrid. Fine. Okay. So let's discuss like what are the major attacks. Sorry, one slide is somehow missing. So that's all right. I thought the dual loop PI controller, but let me. I will also cover up toward the later what is dual loop PI controller. Fine. Uh, See what happens that in case of microgrid, now see this we are considering a scenario in which we have a secondary layer and secondary layer uses the communication. The moment you use the communication, then it is always possible that you can have some kind of intrusion, and that intrusion can also lead to a functions which you really do not want in a microgrid. Right? So see, there are different kinds of attack. If you consider the system which is described by linear time invariant system, then this is one way in which you can describe. Many converters are actually nonlinear. In fact, they are bilinear systems, so that's why they are highly nonlinear in nature. But you can always linearize and get this particular form of system. Like you are obtaining a small signal model for many power converters, so that small signal model will essentially uh, be represented as an LTI system after linearization. And see what happens that there are two attacks which we are going to discuss here: the false data injection attack, and the last little bit we will discuss about the stealthy attack. But let's first discuss the false data injection attack, which is very common. In this attack, what we do, what attacker does, that the attacker will inject, say, some extra signal in your control input. Your control input is mostly duty cycle. That duty cycle also saturates at a certain value depending on the kind of converter you use. So it modifies the complete plant behavior. Now you may be thinking that how come someone through any kind of network communicates to the plant and also modifies. See, most of the controllers, they're connected with the network, and also there is a communication among the converters. So therefore it is also making this entire system vulnerable towards these kind of possible attacks. And there is a possibility that many sensors are also communicating this in. There are smart sensors, then they also communicate this information through network, and it is possible that that can also be compromised. So false data injection attack can happen on your sensors as well as on your actuator. Whenever it happens, then how to identify first, like there is an attack, because sometimes it's very similar signature you get for the disturbances, for parametric perturbations, even the perturbations which occur due to the load change. That is also lead to similar kind of signature. So it is very important for us to identify that this is actually because of some attack, not because of some disturbances. Fine. So it has to remain robust or invariant against all these possible situations which generally occur in any plant. Fine. So we are not talking about very generic case, but we are only talking about this figure is generic in the sense that to discuss what kind of attacks can happen. Fine. So whenever communication system is there, then actuator can be modified or sensor values can be modified. Fine. So that is where you actually compromise the signal. Fine. But how to identify that this is not because of disturbances or this is not because of some other reasons? Fine. That is what we need to keep in mind. Uh, there are other kinds of attack also, denial of service attack and replay attack. This we shall replay. You have to actually store the data, and the same thing you can use so that you can fool the system. But we are only going to discuss first and fourth kind of attack in this discussion, and that is also limited to DC microgrid, not for a generic LTI system. Right? I hope I am connected. Yeah. Uh, okay. See, suppose we consider a simple system with say just a 4 node. Fine. So you have a 4 sources and a 4 converters. So if you see that this is node 1, then node 2 here, 3 here, and 4 here. Fine. Now every node will have its own source. So the source is coming here. You can see the source is here, and then corresponding converter is also available here. Like there is a boost converter, and then what does controller do? Like controller definitely gets information from the neighboring node because you have a primary and secondary layer. Because controller requires what? Even any dual loop PI controller requires a reference. Like you can produce the output of your desired value, but then what is that desired value? That information comes from the neighboring nodes or neighboring agents. Fine. So this controller block is there. This is a typical dual loop PI controller. Fine. This block is dual loop PI controller, and it actually gets the information from the neighboring node. Now, there is a possibility that your actuator because ultimately controller will provide signal to the PWM, fine, like what is the duty cycle. So that can be compromised because this entire thing controller is implemented through some embedded processor. Embedded processor is connected with the network, and also network is used for exchanging the information among the nodes. So therefore, ultimately, there is a vulnerability and a possibility of compromising your either actuator signal or sensor signal, or maybe some other kinds of attacks are also possible on the same system. Right. So, so this is how the system works. So see, what is the basic principle? Most of the work used, like whatever the work available in literature, what is the basic fundamental principle? So if my signal is compromised, is there any other alternate method available for me to estimate that signal? Fine. If my U is getting compromised, U of t is nothing but the duty cycle. But is there any alternate method available with me so I can estimate that signal U hat of t? If I can estimate this U hat, means U of t is actually compromise attack. But by using the system model, if I can estimate this U hat of t and that cannot be compromised, then I can always use the difference of ut and u hat t, and of course I can integrate square, and there are lots of things which I can do with this error, and try to see whether that can be considered as a text signature or not. Fine. This is a basic fundamental principle. Most of the work which are proposed in literature, they use this basic concept. Fine. Okay. So uh, what we are trying to consider right now is the actuator attack. Fine. So we will also discuss the sensor attack subsequently, but our initial focus will be on actuator attack. Fine. So sensors can also be equally compromised, and similar principle we can use for handling that. So what this is the overall system. Like as I said that we have a 4 node. You can see that these 4 nodes are there. There is a load here, and these 4 nodes together constitute the DC microgrid. So they have a cyber layer in which the information exchange takes place in this particular way. one converter is connected with other two converters, not other three converters. So it is not one to all kind of communication. So only neighboring agents do communicate with each other. Right? You can also have some other topology of cyber layer that is completely all right, as long as neighboring agents communicate with each other. That works here. So again, the same thing here, as I said, that is there any way for us, if I am considering the actuator attack, then is there any actuator value is what U of t. This is duty cycle which goes to your boost converter to maintain your required output voltage. How you get that reference? That reference comes from the secondary controller. That secondary controller actually gathers the information from the neighboring agents, and based on that, it calculates the required reference voltage for a given converter. Fine. So but our objective is that ut which is getting compromised, is there any method for me that I can actually estimate u hat of t? So that is a basic thing. So if you see here in this figure, if I just slightly make it bigger, so actuator is your secondary, your PI controller, the dual loop PI controller is here, fine. So this is calculating the control signal here, fine. But in the same thing, you can see that some kind of attack is also modifying the same signal, fine. So what is happening that whatever signal here is going, that signal is actually not correct because it's a compromised signal. But I can use the plant model and use some kind of observer. I hope that all of you are familiar with the basic Leuenberger observer that allows you to estimate the state. The different variants of Leuenberger observer can also allow you to estimate the control input. So we can actually use the functional observer to calculate the U hat. And I is for the ith agent, because you can have a multiple agent. So therefore subscript is used here. That is I is for ith agent. And U hat can be estimated, and this U hat can be utilized in case you can actually determine that there is actually attack on the system, and we can't use the same input which is calculated by the controller. So I can completely bypass this controller and use the observer to implement the controller, to supply the controller. And then I can always run through this functional observer my system. So you can see here there is a switch here, so I can actually switch to your U hat I in place of UI. So I will use U hat I, which is estimated value of control, which is not affected by any kind of attack, and I can use my system in spite of it is being attacked. Fine. I hope is there any doubt at this juncture? I hope you are following what I am trying to say, the basic principle of attack detection.
Yes, sir.
Okay. Yes, yes. Yeah, please go ahead. Yeah.
Is my voice audible?
Yeah, your voice is very much audible. Yeah, please go ahead.
Yes, sir. One question.
Your voice is starting and then after it is fainting. I'm not sure. If somebody or other can hear her voice and repeat the question.
Sir, there is one question.
Mm-hmm.
Uh, are there any MATLAB programming or simulating models available in attack models in grid-tied PV system?
Yes, sir. Sir, is it audible now?
Yeah, yes, it is audible. Yeah.
Ma'am, I told.
Sir, UI, as you have said, due to the actuator attack, the UI value will be changed.
Mm-hmm.
And so the functional observer UI hat is being the alternative path is provided using a switch.
Yes, yes.
Yes, sir. So, but that we can do, like, why to take a risk of having an actuator attack? We can provide a UI hat using a functional observer. If
Can you
can
can you repeat your question? Toward the end, I could not hear you. Like, what did you ask? Toward the end, what
yes,
did
sir.
you say?
Sir, yes, sir, I'm asking that in functional observer, using the state classification techniques, it can replicate UI as a UI that in case of an actual attack using switch, the value of UI is changed. The value I cap. Why to take have me? I'm asking why don't we continuously supply we using functional observer if we are getting an accurate value?
Okay, your question is that then what is the point of using this function? Like, why not to directly supply through functional observer? Okay,
Yes, sir, yes.
your point is valid. Please understand that you will not get very identical performance. This UT and U hat will converge. Whatever you are estimating U hat, that will definitely converge to U of T. That is perfectly all right. Fine. That will happen, but they will not be always zero error between U hat and U of T. So this dual loop PI controller is very standard, and you will only, because see, ultimately you are trying to create one alternate layer. This you may think also that even if controller is attacked, then observer can also get attacked, fine, but many systems do have a certain region in memory. If I am going for the implementation details of this kind of controller and observer, so certain memory locations cannot be modified, and they cannot be augmented even by attacker. So this is more like a safety net you are providing, and this safety net will ensure that if your primary controller is attacked, then you have a like alternate controller, because you see you require a lot of computation here, and when you implement, you will be actually checking this information sporadically, or not that or based on certain event, fine. So if, because this require much more computation, because you have to solve the entire differential equations in real time, fine, because this is using the we will see subsequently that it requires a lot of computation when you design when you actually implement the functional observer. So the best approach is to use this standard dual loop PI controller, and use the observer only in case of attack, because you will not be, the moment you have detected there is an attack, you will also alert the operator, or you will try to see that attacker can be removed from the system, and then after again you operate through your standard dual loop PI controller. You do not want that to be operated through functional observer. Functional observer is only kind of backup which is provided to you, fine. So your question is
Yes.
interesting and valid, but there are reasons for which you can have these two layers of protection, so that otherwise you don't know, if you have only one layer, whether it is compromised or not. So at least second layer gives you that kind of freedom to choose in case primary is getting compromised.
Yes, sir, thanks. There
Yeah.
is a question.
Yeah.
Decentralized, when there is no communication, then the chances of having a cyber attack is very minimal.
Yes, yes. If you, because centralized anyway not used, because there is a huge risk of single point failure. If a single point is failed, then you can't run the system. So centralized, of course, has lots of problems. That gives you very good performance, because the central controller knows the scenario of entire microgrid, like all the converter information reaches to that central controller. But you still need some, because they are not co-located. Ultimately there is a one central controller, and then commands are going, and uh, that may not be connected to the main network, and therefore it is possible that that system may not be affected by any kind of cyber attack, but still uh, that system has several drawbacks, and nobody uses that kind of system where you have a single central controller, and you have all converters distributed in the entire region. But of course that because there is no way you can connect to the system. If there is no way you can connect to the system, then you can't also compromise that system, right? Particularly in case of many confidential nuclear research, they do not connect with the system. They are creating the air gap between the network and their own system. So if there is air gap, there is no way you can actually compromise that system, right? Like in case of, you see that Iran, there was an attack that entire nuclear research facility was having the air gap, but they actually attacked that system by using some pen drives, some viruses they spreaded, and that system got compromised, not because of connected to the internet, but it was compromised through this by infected hard drive was used, or infected pen drive was used, and that is how, in spite of having the air gap, they compromised that system, right? So that's very famous case in case of cyber attack for such kind of strategic nuclear uh, systems which were attacked. They are always under some kind of surveillance and attack. But yeah, your point is valid. In those kind of cases, you can't directly attack in that way. So, but we are considering a case in which the system is connected to the network, and we are trying to see how we can uh, actually replicate the our required signal, and we can still operate in spite of being attacked. Did I answer your question? I hope we are connected. Yeah,
So
okay,
yes.
okay. Yeah, because I don't have any way to verify that. So, okay, let me go to the next slide. See, uh, when we are actually our boost, what is the order of boost converter model? This is the second order, fine. Boost converter, when you are trying to model in state space, so boost converter will turn out to be second order. But if I control the boost converter through simple PI controller, then my total order of the system will become, because I will be using dual loop PI controller. So I have a two integral actions. So what will happen? That will result into the fourth order model if I model controller and plant. So if you see the mathematical model of ith node is this. But this is along with controller. Please keep in mind the state I have. The first state is what? The current state. X1 here is current. Uh, here X1 is with I, means I is for the ith converter. Fine. So double subscript is used for that. But just consider X1 is the state. This is the current. X2 is the state, which is the voltage, the output voltage of the boost converter. And X3 X3 and X4, these are the two additional states. They are the flux state and charge state. So they are coming because we are modeling the controller and converter together, fine, because controller contributes the two integral actions, the dual loop PI controller. Internal your internal loop is the current loop, outer loop is the voltage loop, and therefore our entire model becomes the fourth order model, fine, along with the controller. See, what we want to do here, our objective is to actually calculate that control, fine. Therefore the controller is designed by using the classical method, dual loop PI controller, but the observer I will design by using this state space based method, fine. Therefore we are converting into time domain, frequency domain to again time domain. So these are the equations. So these additional states are x3 and x4. They are contributed because of these two integral actions which we are adding. Now all you know that boost converter is a bilinear system, so it's highly nonlinear. So I need to convert into linear time invariant system. So we have to linearize about the operating point. So operating point you can obtain by uh, considering this x dot to be equal to 0, and you can see that these are the operating point, fine. These capital letters are the operating points also for input and all the states. So now you can actually, these are the steady state values of x, fine, and you can linearize about this steady state value, and this is what you will get as LTI system, fine. The AC part of that, you have a constant part plus that variable part, the AC part, and that is what is modeled here. So once you have this model, then we can easily design our controller. So our controller in this steady state form will be like this, because this, it is fourth order system. So controller contains only this. KP means what? The uh, uh, PI controller means proportional controller for in I means current loop, fine, and V means the voltage loop. KPV means it's a proportional gain for the voltage loop, and KPI for current loop. Right? So same way you have a KIV. KIV is for the voltage loop, the integral gain, and KII for the integral gain for current loop, right? So because we are using the 2 PI loop, and therefore your current. So our requirement is what we have to estimate this fellow, right? This UI we have to estimate, UI tilde we have to estimate by some method. So we are using the functional observer, and then we will take the signature. So this is a dual loop PI controller, fine. See what happens here, it starts from here, fine. This is the outer loop. Reference is coming from the secondary controller, and this is coming from your measurement, fine. X2 is the state which you are measuring at the output of the converter. The error will go to this simple PI controller, and because of that you are getting one extra state is X3. Then it will provide the reference to the current controller. So this reference is here. So reference this reference x1 ref and x1 I. So this reference, what are the error is there, that will go to current PI controller, and then this PI controller will give you one more extra state, that is x4I, and means x4 state and x3 state. X1 we know that's the current, x2 is your voltage, x3 state contributed by this voltage, yeah, so that's a flux state we will say, and x4 we will say that charge state, because you are taking the integration of voltage, so you get the flux. You are here in this case you are taking the integration of current, so you get the charge, and that's why we are denoting it as a charge state, right? Okay, so this is your main controller which will go here, and then this is a pure controller. Then there is a attack signal which will come here, and then after the actual control, sorry, then actual controller will go here, and of course you have to have saturation so that you will never cross that saturation, and then after it will go to PWM, fine. So this is how this dual loop PI controller works, and what is our objective? Our objective is to get the U hat T, fine. U hat T, which is going to the PWM controller from here, and that is what I need to estimate. If I can estimate that, then it is possible for me to bypass this controller, even bypass this attacker and everybody, and I can give the clean controller, fine. So the linear functional observer has advantage that even if you want to say estimate just one state, say one state x2 t I want to estimate, I can design the lower order observer. I don't have to have a full order observer. System is fourth order. I can have a first order observer which can only estimate the x2 hat. I can also design the first order observer which can only estimate u hat t. That is not possible with other classical observers, and also many variants of this observer, because there are large number of observers exist, and with all of them it is not possible to estimate. You will have a higher order observer compared to what you get from the functional observer. So that is one advantage with the functional observer. So see, whatever you want to estimate, suppose this is your system, this is a standard LTI system, this is what you are measuring, y of t is what you measure, right? The dimensions of all matrices are standard. This is simple LTI system, and with of course some kind of d of t you can also treat as disturbance, or maybe you can treat it as attack also, fine. But so there is some exogenous signal, and uh, see what I want to estimate. Say I want to estimate g of t, fine. If I want to estimate g of t, which is nothing but the linear function of f, linear function of state. So if I choose say f to be like 1 0 0 0 in our system, then what I am actually estimating, I am estimating x1 and x3. But if I choose f to be say just 1 0 0 0, then I am just estimating x1, fine. So that is also possible. So I can actually estimate depending on what I want. So I can also design the observer to just estimate one state or two state, fine. So in case of two state, it will have this dimension through which I can estimate x1 and x3. So 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 see, I can also estimate because what is my control? If you look at the control, is nothing but the linear function of states, fine, x1, x2, x3, x4. If you again recall your model, So this is what is your gains, fine. So this xi is nothing but x1, x2, x3, x4. So that will multiply with some constants here. And so these constants, I need to obtain the linear combination of the states and constant, fine. So ultimately k1 x1 plus k2, I can only obtain the linear combination. If there is a non-linear combination, then this functional observer cannot estimate, fine. But I can choose z of t to be the linear combination of these states, and it is possible for me to estimate that, fine. So how to design the observer? So the structure of the observer, I will not go into a lot of details of the observer design, but give you the basic concept how to design the observer. The structure of this observer allows you to estimate u of t, and it can also give you any particular state, fine. Not all entire state vector, but you can also obtain x1, x3, x2, like whatever you want. So the structure is this, fine. So this is z hat is the estimated value of zt, fine. So this is suppose actual value of zt is equal to fxt, and the estimated value of is this z hat. Omega t, treat this as omega, looks like w, but just consider this as omega. So omega t is nothing but the observer state, or wt is nothing but the observer state, and these are the matrices which we have to design. Fine. These are the matrices which are the design parameters we have to choose, so that we can actually ensure that error goes to zero. See what you want to estimate. Say I want to estimate fxt. Fine. F can be anything, as we saw in our earlier slide. So if I want to estimate this, then what I need to ensure that this z hat, the estimated value of z, should reach to z as t goes to infinity, means asymptotically. So the error should go to zero between z hat and z as t goes to infinity. Fine. So how to do that? Suppose z hat estimates zt, then the observer state wt estimates some linear combination of xt. Fine. Because we know that what this z hat also has a relationship with this omega t, right? So what we are doing here, that we are trying to reduce the error between so see another thing I want to say, that when z hat is estimating zt, so at that time omega t also estimate linear combination of xt. We will say that is a lxt, fine. L is a matrix, so L can be a matrix like say k1, k2, k3, k4, and x, your state is x1, x2, x3, x4. So the linear combination is nothing but k1 x1 plus k2 x2 plus k3 x3 plus k4 x4, fine. That is also possible with wt. So what I want, that error between this wt and lxt should go to zero, fine. So the dynamics can be given like E dot t is equal to omega dot t minus Lx dot t. I know the dynamics here. I know what is omega t from the previous equation. So we can write the equations in this way, like if I substitute from the model equation and this equation, if I use the omega dot, I already know that n omega t plus j yt plus h ut, n, j and h are the different matrices of appropriate dimension. Then I will finally get this. So I can see there are many free parameters here with me. So I can choose the matrices of n, j, L I can't choose because that that is not a pre-parameter, but I have a many matrices which can be chosen, n and j, so that this term can go to zero. Even I can choose in such a way so this term can also go to zero, because h is again the pre-parameter, L is a frozen, B is frozen from the system. So but still I can actually design in such a way this matrices so that I can ensure that they will these terms will go to zero. So similarly, I can write the error in z, like between z hat and z. So I can write the error dynamics here. Fine. So if I choose these matrices appropriately, like in this original equation, you see that if I choose them such that this goes to 0, this goes to 0, then what I'm left with, I'm left with only E dot is equal to NET. Fine. Because if I put these conditions, then I can always find the matrices N, J, H, D, E, so that these conditions are satisfied. And if that is the case, and if N is Hurwitz, then what will I am left with? I am left with only E dot is equal to NE. Fine. And same way, E Z dot is equal to I will have a D E. Fine. So see what I can do, that I can ensure that N is Hurwitz. N is Hurwitz means what? All the eigenvalues are in the LHP. And so this E will be stable. E will be stable. It means what? W2 will go to Lx, fine, because that is what you are trying to estimate. So it will estimate that linear function of Lx. Lx we have already seen in the previous slide, that this is what you are trying to estimate. So if I choose this matrices, then you can solve this matrix equation, fine. So it's not like this is very complex. You can always find the matrices which will satisfy this. I'm not going for the full theory of observer design here, but this is very established, and we can actually design such that these conditions are met. And this will ensure that both the error like EZ and ET will go to 0 as t goes to infinity. It's not finite type convergence, but it is asymptotic convergence, and most of the observers actually behave in an asymptotic sense only. And you can actually ensure that the error between the actual function and estimated value of that function goes to 0 as t goes to infinity. So what happens here, I hope that you understand what I'm trying to say here. See, ultimately what we are trying to do, that we are trying to replace this value with this observer, fine. The earlier slide, whatever we discussed, this is what we are trying to do, fine. So if I explain you the entire structure, how it operates now. Okay, let me actually okay, see, there is a controller here. This controller, this is a finite state machine model. Once you design the observer, then after what you have a two things, fine. You have a UI and you have a UI hat. So what you are doing, you are taking the difference of that. After taking the difference, you are squaring that value, and after that you are integrating that. So you don't want to immediately see if there is a difference between that is crossing some threshold value. Ideally, what should be the case? The difference would be 0, because UI hat is the same value as UI, because we have proved that estimated value will reach to the actual value. So in a steady state scenario, when there is no attack, the difference will be very, very minute. That will only occur because of some slight parametric mismatch, and because actual plant and the model may not be very identical, and also some computational issues will create some small error, fine. Otherwise there won't be any significant error between the actual UI and estimated value of UI, fine. But see what we are doing now, but if there is an attack, what is going to happen? See, there are two things here. It is a linear functional observer, and that is giving you UI hat, and the actual controller is giving you UI. So you are squaring, integrating, and then after scaling it, fine. So you call this index as your lambda I, fine. So this index can be utilized. This index can be utilized to detect whether there is an error or not. Fine. So so what we can do here, that index is specified here. You can see this index. So this is the index which will tell you whether there is an attack or not. If this value crosses certain threshold, now you may be thinking that how to determine that threshold. So that threshold can also be determined based on the knowledge of the system, or also some kind of machine learning based method, that what is the typical values under no attack condition and what will happen to its attack condition. You can determine the threshold value which is tolerable and which is not tolerable, fine, so which can lead to, but immediately the moment you detect one time, you can't say that it is attack, fine. You have to see that that function should violate the threshold multiple times, then only you should say that there is an attack, fine. So every time you see it and then after see that it is crossing that threshold, then after, because it's integrating, so it will continuously rise, and then after when you check it one time, you should also ensure that you clear next time, means you can reset that that function, this gamma I, and then after again check whether again it is increasing, rising. So multiple times if that phenomena happens, then only you classify it as attack, fine. So therefore we have a here even small animation. So how many times you should allow here, that is calculated by alpha I. There is a one another parameter. So there are because this system does not remain in the same state, so there are four states. You can see that S1, S2, S3 and S4. S4 means there is an attack. If system enters in that, you can classify that as attack because this has happened multiple times, so then you can reach to state S4. Otherwise sometimes just one time, two time, you don't want to do classify this as attack, and that may be because of some disturbances or some other reasons. So now you can see this is your threshold value of that index function, which is used to detect whether there is a signature function, fine. So we can call this as a signature function. There is a threshold of signature function. If the value remains below that threshold, then you are not classifying that as attack, and these are the clock signals, fine. So those who know finite state machine modeling, they can easily understand that what we are doing. This is the real time clock. When I say anything is a clock signal and s dot t is equal to 1, means it's a real time clock. If it is less than 1, then it's a slower than real time clock. If it is higher than 1, then it is a faster than real time clock. But that is not important right now. In a healthy situation, system remains in S1 state, and whenever there is a violation, it will go to a S2 state, then S3 state, and if this violation is not classified as attack, it will go back to again S1 state. Otherwise it will go back to S4 state, right? So that is only one of the states system can be at a particular instant. So there is a small animation which you can see here. Now you see what we are saying, that now your controller, you can I hope that animation is visible here. Can you see the animation here? I hope I am connected, student.
No, sir, no animation is appearing.
So you can't see here this here what you can see this slide in which
Yes, sir, slide is visible.
okay, so somehow this animation is not coming. So nothing is blinking here. Okay,
Yes, sir,
so
yes, sir, it is blinking. No, yes, sir.
okay, now you see when there is an attack, then you will see that see this side in the leftmost corner, that value is crossed this lambda maximum. So now it is crossing, you see that, but one time crossing, you do not want to classify this as attack. You see it has crossed two times, then again it will cross. So suppose you are keeping alpha is equal to 3 or 4, so depending on what is your alpha, you will classify this as attack, fine. Then after it will enter into the four states. You can see here multiple times the this function is crossing this lambda max, lambda I max, fine. Sorry, gamma function, not lambda. My apology. Just read it as a gamma function. So that is actually crossing multiple times, and so alpha you will decide 3 times, 4 times, or 50 times, whatever is applicable. So whenever it crosses multiple times, then only you will classify this as attack, right? So that is why this kind of model is developed. So we will briefly see how to evaluate this concept. So we had 4 nodes and also 1 kilowatt load was there. This is laboratory scale validation. So we use the real-time simulator to control this multiple DC to DC converter, all are boost converter. And these are the experimental plot. now you can see here that we have a attack on node number 4. So U4 is so it looks completely all right. Now at this juncture, if you see, we have an attack. Fine. At this juncture, when attack started, so this U4 has completely modified. But U4 hat, if you look at in the same, it is modified, but not much. Fine. It is not affected much. The current from that converter is also significantly modified. Fine. So all these things are happening because there is an attack. So what we can do that at this juncture, what we are trying to do that we are now switching actual controller to estimated value of controller. Fine. So actual controller is still under attack. You see actual because attacker we can't remove because that is still under attack, but our system can operate even with U4 head. Fine. So the moment you do that, so the current was going in all the directions. So that current after some time it has recovered, and you can see that the current from here it is becoming almost same what earlier case. Right, so what was earlier case was 5.3 ampere, eventually it becomes a 5.3 ampere. The I2 I4 and I1 I3 are 2.65 ampere. Fine, so sharing is happening as per this proportion. Fine, not necessary that all should share equally. You can decide that how they supposed to share the power depending on their their sources or their capability. Fine, so bus voltage is also slightly affected here, but after that you can see that everything is normal. After once we have switched at this instant, we have switched to uh, uh, observer, and observer estimated the value. Right. So same thing you can see here. What happens to this alpha and this function gamma? So so you can see here this function is actually increasing here. It is crossing multiple times. So when alpha reaches to the alpha 4 maximum, at that time it takes the decision to switch from actual controller to estimated value of controller through observer. And after that, you can see that it remains completely normal, right? It regains its earlier value at which it was operated, and but actual attack is still happening on the controller. Fine, so it is not like we have removed the attack, but we have detected, and still we are in a position to operate the system with that attack. Fine, attack is still happening on actual controller, but that is not affecting our operation. So that is why you can see that this is continuously rising, right? So because the system has entered in the fourth state where the attack is classified as attack, an attempt is classified as attack, and then system is operating through observer state. Okay, so we can actually see the previous observer what we use. That observer can also respond towards the noise, and also can become very sensitive towards the disturbances. So now we will do slight bring the robustness in the observer itself. Fine. So earlier observer was not robust, but it can definitely estimate the state as well as control input, but we can actually bring the robustness in the same observer and try to make the system more overall robust against misclassifying the attack, right? So so false positive we can reduce. You know that when you are estimating, you also have a possibility of even there is no attack, but you are still classifying that as attack, and that can lead to false positive. So and to avoid or to reduce that false positive, then we can actually use we have a similar system, the whatever system we did earlier, but on the observer we will bring the robustness here. The same system, same model is again here, and this is how we are defining the through this xi variable we are defining the attack. When there is attack, the model is same the what we discussed earlier, but only this I wanted your here we have a two kinds of attack happening together. The state attack, the false data injection in state, and also false data injection taking place on input. So if you see that observatory equations are same, but it has an external injection term, some additional injection term, that is a signum function. So this is a sliding mode functional observer. so that that sliding mode controller itself brings you a lot of robustness. So sliding mode observers also bring robustness, so that is what is carried out through this sliding mode functional observer. And we have a two observer here, like one is for the voltage sensor, because the attack can also happen on state x2, and this is actually carried out through this another observer. This is only one dimensional observer. So compute, because remember, keep in mind that this entire equations we have to solve in real time, fine, in our whether you use microcontroller, DSP, whatever the embedded platform you use, you have to solve these equations. So therefore, the dimensionality is also important whenever you are going for observer-based solution. So functional observer normally turn out to be of lower order. Most of the cases, that is the scenario. So you don't require to solve multiple differential equations, but if you are estimating u of t, then you have to solve only one. And if you are estimating, say, one state, then you require again one differential equation. So solving first order differential equation is much more simpler compared to solving, say, four differential equations which are coupled, and that will definitely take more time compared to one differential equation. So these differential equations you have to solve because that represents the model, and that you need to solve, right? So again, here we have a dual loop PI controller, but only the difference here is we have a sliding mode based functional observer, which actually works much better compared to the earlier results what we discussed. So I'm skipping the entire formulation of this because it is very similar lines, but sliding mode has certain nuances and differences which you need to take into account when you are designing the sliding mode functional observer, right? So see, again, the same thing here. You have a finite state machine model for the two scenario. One is for the actuator attack, and also you can have a sensor and actuator attack together. So system will be in one of the states. Like if you consider actuator attack, we are calling the states as A1, A2, A3, A4. Whenever the attack is classified as attack, then you will go to the A4 state. Otherwise, mostly the healthy state is A1. You will be in A1 state, and different situations will trigger the transition from A1 state to A2 state, and then A2 state to again back to the A1 state, or A2 state to A3 state, right? Or if there is a persistent attack, then it will go from A2 state to A4 state. So same thing also happens for the sensor. So for sensor attack, your system can be either in S1, S2, S3, or S4. So depending on your situation, whenever you say that there is an attack which is classified as attack, then you will actually go from S1 state to S2 or S3, and then finally you will reach to S4 state if that classified as attack, fine. But there is a sensor attack, and so you can be in a healthy scenario A1 state and S1 state, fine. For sensor it is S1 state, for actuator it is A1 state. So that's a healthy state, and most of the time system will keep operating in that. Only during the attack it will transit from A1 to the corresponding state, only for a momentary, or it is some kind of disturbance, or it is actual attack, then it will go to the permanent attack state. And then you will also switch from your actual sensor measurement to the observer sensor measurement, or actual control input to the observer based calculated control input. So you can switch to there, and this all work is actually published. You can also see our paper. I am not going into a lot of details here, but trying to give you the overall glimpse, particularly how to detect the attack. See, this is what, as I said, that this is a basic fundamental. Like this is the signature function, and this is for the state. State we are not integrating, but for input we are doing the integration action, so that you get more reliable here. But state, what happens that state values cannot differ too much significantly. So there you do not require because u is continuously calculated and continuously modified, but x2 is kind of very like whatever, suppose you are maintaining 380 volt or 120 volt, so normally it remains close to that value, and lot of changes are not anticipated in that value. The moment it happens, then immediately you should act, it should be more sensitive towards the small changes also, and therefore this kind of function is used, signature function is used to detect that attack. So one is the estimated value. You can see that this is always happens. One is the actual value minus estimated value, and the difference will actually drive your decision to classify that as attack or not. But only your estimation should be very accurate, or at least as close as possible to the accurate, so that you can take the right decision and reduce the false positive, false negative, and all those things can be reduced. This was also tested on similar kind of setup, but here you can see that there are multiple attack also happening together. Like see both, I can show you that here attack on node 3 starts here, and then there is another attack, which here it is happening both on UIL and for multiple. Here we are showing that what happens with during the multiple attack. Fine. So attack on node 2 starts at this particular junction. Attack on node 3 starts at this juncture. You can see, and still the system actually can be restored to the healthy system by using the observed value. So the moment you switch, then you can see what happens, that this becomes very smooth and again it becomes normal in spite of having the attack on more than one system. You can also see what happens to the this functions, the signature functions what we have. You can have in sensor, you can also give as high as 15-volt attack. So ideally all this output voltage VC1, they are the capacitor volt across the capacitor. That's why we call it as VC1, VC2, VC3, VC4. Four nodes are there. So they are like very close by. The moment attack happens, you can see that the attack is happening on node number 2. So the color for the node is this, and you can see that it has already gone from here to this value. So it is very, very different than what it should be. It should be somewhere here. And then there is a minus 15-volt attack is also there. So minus 15-volt attack is actually taking the things here in the negative direction. It's not negative, but I'm saying that the voltage is significantly reduced because of this minus 15-volt attack. And the now what we are doing, you can see that controller is switch at this instant on your sliding mode functional observer. And at this also we are switching, controller 3 is switched to the sliding mode functional observer. The moment you do that, you can see that the things are becoming much smoother, and once both are switched to the observer from here onward, you can see that they are again becoming normal. But during attack scenario, they are going in a very, very different values. They have a significant offset, whatever the offset is added by the attacker. So those offsets are reflected here. But the moment you actually switch both the controller, because there are two attacks happening here, once both the values are restored by their observed value, they are again become behaving normal after some transient. So this also allows you to like even because robustness also comes because of this sliding mode observer. And you can see that in spite of not using the actual parameter, like capacitor was whatever we are using for the design and actual both are different, still it does not affect your estimated values much. Fine. So no fluctuation you will see here. Capacitor is 20% increase or decrease, on very minimal fluctuations are there from the nominal values. So that is the robustness which is guaranteed by sliding mode observer. Similar robustness you can't get from the standard functional observer which we discussed earlier, but this provides you slightly better result in terms of its sensitivity towards the noise and parametric variations. So we will briefly see that covert attack are like very, very difficult to detect. These attacks actually happen in a way so that they remain hidden. Now also I will explain that what is the principle, because in your u of t, if you add, suppose if I say my pure control is up and actual control is u of t. If I add very small value ua of t, very small value, it will never saturate. Then it's very difficult for me to detect that there is an attack. Fine, so it always remain hidden. So how to attack such kind? How to detect such kind of attack? So now we will only discuss about detecting such kind of mechanism. We don't have any way to mitigate them because they remain very much hidden. So, but this is very interesting work in the sense that uh, we can use the structural property of the system, right? This is perhaps the first of its kind which uses the system's behavior to determine that whether there is a covert attack taking place on the system or not. Again, we are taking very similar kind of system, but treatment is very different here. The treatment, we are not using any observer, we are using the system's inherent properties, the basic fundamental properties of system, which allows us to detect this attack, covert attack. Fine. Now, conceptually, what happens that, see, this is the attack we are trying to discuss, like the attack which is happening on actuator or attack which is happening on your sensor. So focus will be on sensor attack, actuator attack here, but we can also use the similar treatment for the sensor attack. But covert attack we are talking about, fine. So we will provide a robust detection metric, fine. So you calculate that, and if you say that if it is like not equal to 1, if it is below 1, then you can say that there is some kind of problem in the system. It may be some kind of attack, not necessarily that every uh, uh, signature will lead to attack only, because sometimes such kind of attack, particularly covert attack, are slightly difficult to detect. And so again, finite state based machine model will be provided, and so we will use this same as 4-state model representation for each microgrid node, and every node is controlled by dual loop PI controller, which is very established controller for most of the power electronic system. Rather, I would say, at least in DC to DC converter, dual loop PI controller is very established methodology to design controller, but it is not limited. You can have any kind of controller, you can still detect that, right? So internal state can be utilized to detect. As I said, that this uses the structural property of the system, and I will actually explain through concept. Again, I have a small animation. I hope that should work. See, your control is what? Again, if you look at the same figure I am using here, that you start from here, you calculate your control here. Fine, this is your pure control without any kind of attack, and the UI is actually combination of both. So ui is nothing but the addition of this plus this, fine, is equal to ui. So what happens here, that if you add ui, then you remains again the whatever is required. Okay, so now you see that if you are increasing uia, can you see the animation here? Hope I am connected. Hello.
Yes, sir, you are connected, but no animation can be seen.
Okay, you can't see the animation, but can you see the graph here?
Yes, the slide has been changed.
So what is the title of this slide? Can you read just?
Uh, DC architecture for covert attack detection.
नहीं नहीं, then तो it is. अच्छा, no, are you not getting? No, that is the next slide. How actuator attack may remain covert. Are you getting this?
Yes, sir. Yes.
But can you
Yes, sir.
see
Now
any
I can see this. Yes, sir.
animation
Now I
is?
can see. Yes, sir. How the actuator attacks may remain covert.
But can you see the animation also here?
No, sir. No, sir.
Okay, but I hope whatever I am writing. So what I am trying to say, that say UI is equal to UIA plus UIP. Fine. If I increase this, then this fellow will decrease. So the net will remain same. Fine. If you if you if you decrease this, then this fellow will increase, and still it net will remain same. So there is animation, but somehow it is not getting projected. So what I am trying to say that they always remain a covert. So there is no way directly to detect that this kind of attack. So we need some kind of function. See, if I create some kind of function, so this function should respond only to UIP. Fine, UIP is my pure control, but this should respond in a differently whenever there is a UIA. So can I create any function based on the fundamental properties of the system? Fine, that is the question here. Can I create that? Because uh, by observer or by any method, it is impossible to detect the way they behave this kind of attack. And because see, ultimately, whatever you are giving here, so the net control is going. So ultimately, what will happen if this fellow UI is injected here? So this will go down. This UIP will go down when UIA is going up. So the net will be always same. Fine. So therefore, if it is say injecting zero point 0.1 unit UIA, so then UIP will go 0.1 unit down. So therefore, there is no way for us to detect that this what, because there is no problem to the plant. Plant is perfectly functioning properly. So, but still you don't want this unwanted kind of input which is provided by some attacker. You want to detect it. So that is why we call it as a covert attack, because it is remaining hidden. And how to detect it, right? So again, so I have changed the slide. So the architecture is similar, only we are trying to create a metric which should respond to the this kind of attack. Right? That is what is the main purpose of this particular work. So we are talking about this UIA coming from the control is UIP. The superscript is used here, and the total signal is nothing but UI, which is the addition of two signals, UIA and UIP. Right? And PWM signal, so PWM signal will go to here. It will remain same because it doesn't know it is coming from part of the control is coming from attacker and part of the control is coming from UIP. UIP is modifying depending on what attacker is injecting. So therefore UI doesn't have any way, you can't detect this kind of attack. Fine. So therefore we have to rely on system property, that how system behaves. Fine. So we okay, so there is a metric here. So this function, this metric we can calculate. See this function, if I, what is m here? M is this V input divided by x2. This KI is nothing but the gain of PI controller, which is used for inner loop, integral gain. Fine. There is an inner loop and outer loop. So the same way it is here also. But if you put the value of m here in this is okay. How it has come? This has come because of certain structural property of the system. Because it has, you directly it is written. So some of you may not directly get that what is this suddenly. So X4 is the state, Ki is actually the gain of your control loop, the PI control loop, inner current loop, and then gain of integral part of your PI controller. And if you simplify this, because we also know that U of t is equal to UP plus UA, right? So this is true for all the nodes. So if I want to put the node, I can put here, fine, subscript. So if we use these two equations and put here, because this can be easily calculated. See, this cannot be calculated, please understand, but these two are equivalent. This value I can calculate, fine. This value I can calculate, or I can calculate this value, because my this metric can be easily, because everything is known to me. I know what is m, I know all this x4 ki I1, all the values I can calculate, but this is nothing but equal to this. Now if you look at this, if there is UA is equal to 0, then this metric will be what? 1. If it is non-zero, UA is say non-zero, it is very small value because it's a covert attack, then this will become less than 1. Or maybe if you want to write in percentage, then it will be a normal situation, it will be 100%, and it will go less than 100% in abnormal situation, or when there is some attack or some kind of problem. So if you look at The M is not a duty cycle, please understand. This is the input by output. So normally what is the value of M? Because it's a boost converter, so this X2 is normally higher than input, or it can be equal to that. So normally M is less than 1, fine. So so if you look at this metric, then you have actually some safe operating region. So ideally it should be 1. You see that this is where it should be. But you can say that, okay, even if it is close to 1, I will consider this as a healthy situation. But whenever it crosses this threshold, and for a different values of M, there will be different curve. But ultimately, they all will be reaching close to this 1 whenever there is an attack. Fine. Whenever there is a healthy situation, it will be operating in a very narrow region here. But whenever there is some kind of attack or some kind of problems, it can actually deviate from here, and that you can class. So this is the structural property of the system, and therefore it is kind of invariant to the lots of variations otherwise take place in the system, and it gives you very robust performance in terms of variation. Here also I have animation, but I am not sure it will work. But can you see animation here? So you can actually calculate this value. You see, for here you have all the can you see this finite state machine model here in this slide?
Yes, sir. Yes, sir.
Okay, if animation is
Yes,
not
sir. We can see it.
okay. So so what happens at the moment you can once you classify that this metric is going below 1 or below 100%, so you may tolerate it 95%, still 90%, but if it goes below that, then you may want to classify this as attack, and you can actually say that it's a covert attack which is detected here. So it will go into the normally it will remain in S1, but if there is something detected, it will go either S2, S3, and again go back to S1. If that something, whatever was detected was only momentary, but if it remains longer, then it will actually go to S4 state. So you can see here that when there is an attack, this function will go down. There is a threshold, and this threshold will be crossed. How many times the threshold is crossed, and based on that you can take a call whether to classify this as attack. There is no way to always say that I will have a like 100% assurance of classifying some event as attack. Fine, it may not be attack, still you will classify as attack because there is the possibility of having the false value. Fine. Okay, show some experimental validation. You see that this is given in percentage, so all the metric for all the converters, like because there are 4 converters, so you have to compute the metric separately for all of them. So for converter 1 it is 100. See, when there is attack, it has gone down. Fine, you see that it is going from 100 to a somewhat lower value here. At this juncture you can see attack on node attack is on node 2, so it is going down. The node 1 also getting attacked, so it is also going down. So when there is an attack, this metric will go down, and based on that you can take a call. You can keep your threshold. How many times is going is determined by alpha, like 3 times, 4 times. So the moment it crosses some threshold, because you need to take a call at some point of time that now it's attack, so you need to classify that as attack. So this counter is only for to doubly assure multiple times. You want to assure that this is attack. That's why there is another counter which is utilized here. Uh, so I think I stop here. If there are questions, I can take questions. So this work, what I presented, was actually from my student Himani Modi and Mohit Kachwa. So most of the work is actually done by them, but the entire setup and other things was also created by other student. So Mohit is already graduated, and Himani is like on the verge of completion, and Mahesh Nehra, he is also one of my students who supported me. So I would be happy to take some questions if you have any questions at this juncture.
Yes, to all the participants, if they have any question, then they can ask. They can unmute themselves and they can ask. Sir, I have a question, very small question.
Yeah.
So in the previous slide, with the variation in m which is v upon v naught, then there is variation from 0.4 to 0.6, and the curve was getting wider. So does value of m also affect the value of u, which we were calculating? Like it was deviating from safe region.
Yeah, see, ultimately the ideal value will be always one, irrespective of this, because you can also normally boost converter, you can go output voltage can be 4 times your input voltage in a normal scenario, but it can go even higher than that also. But if you look at this equation, see, irrespective if this fellow is not present, if UA is this 0, then this will be 1 only. But even if suppose it is very small and say m is also because the m can be anything less than 1. So if m is say close to 1.8.9, so it is possible that this value will be slightly not 1 but slightly closer to 1, right? So that is why these curves are becoming like that. But see, we are not saying that the moment you say this is the operating point 1, the moment you cross, we can never classify this as attack, because we have to give some safe region of operation. So this is the one region in which you are operating. So that's why we are saying that within 10% variation is fine. So within 10% we will say that system is operating in a healthy scenario. There is no attack, or there is no need to calculate anything more to see that there is attack or not, because you are correct that your observation is that this curve will change depending on the value of m, because whether m is equal to zero point 0.4 or m is equal to zero point 0.6, so zero point 0.6 will have a wider, so you need to provide slightly higher margin for zero point 0.6. That is correct, so that needs to be done. But still what we are trying to say, this is theoretically that if UA is not present, then value will be close to 1 irrespective of value of m. But as I said that the UA is also because of some small disturbances, computational error and other thing, and that's why you need to take this thing into account.
Yes, sir. Thank you, sir.
Yeah.
Is there any question from the participants? Sir, one small question, but it is related to droop control. So when we consider the effect of line resistance in droop control, and if we take a different line resistance for two different converters, then will it affect the droop? Will it affect the current sharing when droop control is also applied? So due to line resistance, like difference in line resistance, will it affect the current sharing?
Yeah, of course. See, what I explained was like in a very idealistic scenario, just to give you the essence or feel of droop. But lines will have their own impedance, and that will definitely affect. In fact, the lines which are having higher resistance, so that converter will contribute less, because terminal voltage will be less. Even if two sources are giving the same current, but if one has a higher resistance, then terminal voltage will be less, so that source with a higher line resistance will contribute less to the power. That bound to happen.
Okay, sir. Thank you, sir.
That is why you require this secondary layer controller where the neighboring nodes at least communicate, because Droop is very simple. Without communication, it can function. But at the same time, you should know the model so that you can tune your Droop values appropriately, because their line resistance is not changing dynamically. Like today is say 2 ohm, tomorrow it will not become 2.3 ohm. So it will remain same. So if you know a priori, then you can always design in a such a way so it takes care of all these line resistances. The design part, you can handle that line resistances. So you can still operate the system without need of communication. But you are not sure, like if something is dynamically changing, in that case, neighboring communication is the best solution.
Yes, sir. Thank you, sir. Thank you.
Thank you.
There
So
is
I'm
any
just
question? Yes. Sir, I think there is no question. So one question, chat box.
Mhm.
Okay, it is just saying, are there any MATLAB programming or Simulink model available for attack models on grid type?
MATLAB means you can develop. I believe that if you know the equations, then developing MATLAB model may be available in there. They provide several sample models. So I'm not sure about that. But I believe that once you know the equations or once you know the modeling equations, then you can easily model anything like grid tied inverter or any other thing also you can develop. I'm not sure whether MATLAB provides in that way or not, but developing is not difficult. I would always prefer to develop your own rather than using someone's model, because in that you don't even sometimes know how it is not created. So if there are no questions, then I thank you all, and now I will log out. Thank you.